Yeah.
Okay, this next one, I'll just get these beams displaying as lines. So in this case, the yeah, so in this case, we've got the bending moment diagram for the main longitudinal beams is showing a large negative moment at each end, whereas that should be close to zero. And also we can see that we've got large bending moments in these three beams here. The adjacent beams had much smaller bending moments. And the problem here is we can shut down the results. And we'll zoom in and look at the beam connections. So if you look at this transverse beam, you can see that this end of the beam here is not actually connected to the longitudinal beam. The same for all the other beams across. And the easiest way to check that is over on the toolbar on the left. There's an icon for show beam free ends. So if you click on that, you should get a message saying no beam free ends found, but in this case it found 135 of them. They're highlighted there. So the easiest way to fix that is actually to delete all of the transverse beams and then create them again and make sure that the connections at both ends are okay. And then that will give the correct result. But that just does illustrate that these sort of things are quite easy to miss if you don't select that option and looking at the whole model. It looks fine. It's only when you look right close up that you can see there's a problem there. But when you look at the bending moments, it is obvious that there is something wrong with that model. So whenever you do a computer model, it's very important to have an idea of what sort of results you're expecting. And if you get something that looks like it's obviously wrong, then you need to investigate and find the reason for that. Okay, then the last one was in this case the bending moments from the end diaphragms, the problem type 2, was quite a bit lower in this model than I was getting in my model. And it turned out there were two reasons for that. The first one is the property for the dimensions for the beam. So we go into beam properties. The geometry. Click on the shape there. So now I've set that beam to the correct dimensions, but in the model set up, the depth had been input as 0.9 rather than 0.95. And that's a very small difference, but the stiffness of the beam is proportional to the depth Q in the formula for the second moment per area. So quite a small difference in the depth. makes a significant difference to the stiffness, which affects the bending moment that's generated in that beam. It doesn't make such a huge difference for the longitudinal members because they're directly loaded. So the bending moments in the longitudinal members is really governed by the position of the load and the magnitude of the load. But for the end diaphragms, the bending in these really depends on the amount of twisting from the longitudinal beams, and the bending moment generated by the twisting depends on the stiffness. So the transverse members are more sensitive to the stiffness. The other point was that the position of the response variable. So let's just go to the live load case, and for the end diaphragms, for the first run we did, the response variables for moment and shear were set up on that position here. So when the computer generates the load position to get the maximum bending moment, it would actually find a position that gives the maximum bending moment at that location. But that's not necessarily the maximum bending moment anywhere along the end diaphragm. So there's two ways we can handle that. One would be to put a response variable on every member along there, and at each end of every member. And that's okay, but that just generates an awful lot of different load cases. And another way we can do it is look at the worst case with the response variable in that location and find which beam along the end diaphragm has got the maximum bending moment. And doing that, we find that it's this location here. So then we can insert the response variable at that location. We can either move that one, or in this case I've inserted a new one. And then having done that, we need to go through the whole three-step procedure again. So having inserted some new response variables, and we should do the same for the top slab. I believe for the top slab that the locations we originally used were the correct ones. And for the main longitudinal beams, our midspan locations there were also the locations for the bending moment. So it's really just for the end diaphragms that we need to change the position of the response variable and go through the process of generating the load positions. So run the load influence solver, then go to the results, loading the combinations, and finally rerun the non-linear step analysis with the new load positions. And having done that, we should get the maximum bending moments here should be similar to what I was getting from my results. So we'll just look at the results from that. So yes, so I've rerun that with the new response variable there, and we're getting I'm getting the same results as I got from my original run from that, and that's loading from 22. Okay, so that was the three problems that came up last week, and there's some notes on those on Moodle if you want to have a closer look at that. Now I want to have a look at having completed the analysis, have a look at how we can extract the results from that in a suitable format for the design report. Okay, so this is the model from last week. This has been set up for the ultimate state. And first of all, let's look at the bending moments in the longitudinal beams. So on this display here, I've just hidden the other beams by clicking on the tools shown by type property and selecting just beam type 1. So then we can open the results. So we need to find the load increment that gives the maximum bending moment, which in this case is number 19. You're right, you may not have exactly the same increment, just depending exactly on how you set up the different load cases. But find the one that gives the maximum bending moment. Make a note of the beam number there, which is beam number 116. And then we can find that beam. We press Control F, Control Find, and type in the beam number. Select beam. So we can see that's the third beam in from there. So what I want to do for copy into a spreadsheet is to extract all the bending moment results for that line of beams along the third girder in from the right. Before I do that, in the same way as we did for when we did the peer analysis, I want to give each beam an ID number to make sure that they're sorted in order from left to right. So to do that, you go to the attribute, the ID, and for the ID value I'm going to type in X, which will mean I'll give the ID value will be the X coordinate of the middle of the beam. So I can now select all the beams and add the ID. And the next thing I'm going to do is I'm going to select that line of things, the third one in. Use the select my region button. Click on either end. Okay, so I've now got that line of being selected. So now I can open the results. And click on the results listing icon. Select beams. Select force and moment down bottom. Then I want to filter on selected beams. I want increment number 19 down here. And then the columns. I want to see the ID. Shear force 1 and bending moment 1, and the shear force 2 and bending moment 2. Click on the ID column to sort that file. Order. And then I can then copy those results into spreadsheet. So I'll just go and open up So this is actually a result spreadsheet from last year. I'm not going to give you this one today because it's got last year's results in it, so it will be misleading. But what I'd like to do is to set up something similar for yourself, and this will be actually updated should be for next week. So we can paste the results in there, but to avoid upsetting the formatting of the table, we can go into the results listing here. Press Control A to select everything. Then right click and copy including fixed cells, so we get the headings up to the top and down the left. And then we can place that in the description. So then you can copy that information. Okay, so that was for the longitudinal beams. We can go through a similar process. We also need to look at the end diaphragm results and also the transverse topside results. Okay, so that's a summary of the process. I'll leave it to you to try for yourself now, so any questions, let us know.